With this, we are ready to apply the Riesz Representation theorem to this positive linear function of I. With the Riesz Representation theorem, you can find the version we are using in full-length real analysis, second edition, page 212, section 7.2. This is the version of Riesz Representation theorem we are using. There exists a unique Radon measure, mu on G, such that I of f is equal to the integration of f against the measure mu over G for all f compactly supported and continuous on G. Another version of the Riesz Representation theorem is about replacing this complex supported condition by the vanishing at infinity condition. But the version we are using is this. Now, it remains to verify that this mu induced from the Riesz Representation theorem is left invariant. And we're going to prove this in two steps. First, for any u open in G, we'll prove that mu of x times u is equal to mu of u for any x in G. To prove this, we're going to use Urysohn's lemma together with the monotone convergence theorem. And I want you guys to watch this part carefully, because this should appear again in the proof of uniqueness for Haar measure later. So let's see how the Urysohn's lemma and the monotone convergence theorem are applied in here. The key idea is to use the inner regularity on open sets of Radon measures to approximate this open set from inside by compact subsets. The procedure of approximation is the following. Since mu is irregular on open sets, there exists K1 contained in U such that mu of U minus K1 is less than 1. We can do this. Now, by Urysohn's lemma, I should emphasize this is a compact subset. This K1 is compact. By Urysohn's lemma, we pick F1 compactly supported and continuous on G with the support of F1 contained in U, and F1 is between 0 and 1, and F1 is constantly equal to 1 on the compact subset we described in here. So this is our first step. And the second step, we pick F2, compact supported on G and continuous, and at the same time, the support of F2 is contained in U. F2 is between 0 and 1, and F2 is constantly equal to 1. On some K2, where K2 is a complex subset containing the support of F1, but at the same time, it is contained in U with the complement of K2 in U having measure less than 1/2. Do you see how to construct such K2 specifically? First, you just pick any K2 whose complement in U will have measure less than 1/2 by the inner regularity of U. And then you take the union of that K2 and the support of F1. That is how you construct this K2 containing the support of F1, but at the same time is contained in U. And you apply the Euroson's lemma with respect to K2 and U to find this bump function F2, which is constantly equal to 1 on this K2. That is how you do the construction specifically. Then it follows that F1 is less than or equal to F2. Do you see why? This is because F2 is constantly equal to 1 on K2, but the support of F1 is contained in K2, namely F is equal to 0 outside of the K2. So F2 on K2, which is constantly equal to 1, is greater or equal to F1, and outside of K2, since F1 is 0, clearly you have this inequality. Now you're going to repeat this procedure. So we get an ascending sequence, F1, F2, F3, all the way Fn. They are all between 0 and 1. With Fn constant equal to 1 on Kn, and mu of U minus Kn is less than 1 over n. The support of Fn all contained in U, and Fn, of course, are all compactly supported. And now we make a claim. We claim that the limit of Fn's as n goes infinity is equal to the indicator function on U, mu almost everywhere. And let's verify this claim. Now let's prove this claim. Indeed, if you look at the indicator function on U and the indicator functions on those k sub n's, since by our construction f sub n's are all constant equal to 1 on Kn. So fn's are greater or equal to the indicator function on Kn. So this is less than or equal to f. But at the same time, so this is less than or equal to fn. And fn is in turn less than or equal to 1 over u, because the support of fn is contained in u. So this is because fn is equal to 1 on Kn. And this is because the support of fn is contained in u. And we have this approximation as n goes to infinity, because mu of u minus Kn by our construction is less than 1 over n for any n. And of course, you should think of this as mu almost everywhere convergence, as opposed to pointwise convergence. But that's enough for applying the monotone convergence theorem. So, mu of xu, which can be written as this integral, is equal to, if you put this x inside and make a change of variable, this is the same as the integration of the indicator function on u of x inverse y d mu y. Here, y in xu is same as x inverse y in u. And now, by the monotone convergence theorem, and the limit in here, you get this guy is equal to this limit of fn's. And now you pull out this x inverse. This gives you L sub x inverse applied to fn acting on y d mu y. And this part is I of L sub x inverse applied to fn. But we already know that I is left G invariant. So this is same as I of fn. This is by left invariance of I. And this last line will be, if you reverse all the procedures above, you can see easily that this is equal to the integration of the indicator function on u against mu, just by reversing the procedures above. Again, here is the monotone convergence theorem again. And the last line gives you mu of u. So we have proved that mu is left invariant on the open subsets. Here u is any open subset. This finishes our step 1 of the proof of left invariance of this radon measure mu induced from Riesz representation theorem. Now step 2 of the proof of left invariance of the radon measure is the following. For any E, which is a Borel subset on G, we want to prove that mu of xe is equal to mu of E for any x in G. To this end, we're going to apply the outer regularity of radon measures. By the outer regularity, the measure of any measurable subset is equal to the infimum of mu of u's, where U contains xe and is an open subset of G. So this is precisely a statement of the outer regularity of a radon measure. And this guy, by our step 1, remember in step 1 we just proved that mu is leftly invariant on open subsets. So now by step 1, this is equal to the infimum of mu. Let us move x to U and take an inverse. They are equal by step number 1. Next, we're going to do a change of variable in here. We change U to x inverse U and free E from x. And this guy will be simply equal to the infimum of all possible mu of u's, where the U contains E being an open subset of the topological group G. And using the outer regularity again, we get mu of E. So this again is a outer regularity. So now we have proved that mu is left G invariant on any Borel subset. So mu now is a left invariant radon measure. This finishes the proof of the existence of Haar measure on a locally compact group. So we are done with the existence.